Okay, can everybody see the screen?
Yes, Prof.
Okay. So this afternoon, I will share some of the content that I have used when I presented at a conference they call International Conference on this biomedical engineering, in which I discussed about the plasma diagnostic. So, of course, we have this term of plasma diagnostic. So, I hope everybody is in a good condition. All right, so this was, okay, later I will share again, because this is just a link. When I do a conference, most of the time, I will share the link so that everybody can get the lecture note or the slide of this presentation, so that so you don't have to capture or to memo or to snapshot the screen. So that I will share everything on the slide with the audience. So most of the time I will create a link, so I will share to them the link. So I think last time I didn't present about my research lab. So this is my research lab. We call as a plasma processing research laboratory. So me as the head for the lab, and okay. And then we have Dr. Riaz Muhammad Ali. He's also one of my previous students. He did his degree and master in UTHM in our university. He did his master with me. And then after he got the master, he was recruited by the university and he did his PhD in Japan as well. He was in Osaka University in Japan. And now he came back to the university and working with us as a team member in our lab. And I have two postdoctoral researchers. I missed the name over here. This is Dr. Arif Khan from Pakistan. And this is Dr. Megat Muhammad Ihsan. He was the postdoc. Now he already, just about last month, he got the appointment as a permanent staff at the University Malaysia Sabah, which is in Borneo in Kalimantan, near to Kalimantan. So now he just moved to this Sabah. And these are all my students, which is our team member. So I have one guy working as a PhD student. And I have Anis, Yasmin as a PhD student, and then Mulyana already graduated, now working with a company, Infineon, called Infineon, a semiconductor company in Penang, in northern area of Malaysia. I have Nana, is a PhD student, attachment in our lab. So originally he is registered with University Pertahanan Nasional Malaysia, so one of the university in Kuala Lumpur. But she did the attachment with us. So most of the time, 90% of her time is in our lab. And we have Afika, a master student, and Najiha as a research assistant. Okay. All right. When I did the presentation, sometimes we want to discuss about this is the growth of or the evolution of television. So where we can see in 1930s, the television was big like this one, and then the screen was black and white. I think until the 1950s, and then the color television, I think it started maybe around this area. Until now, most of us are using the flat TV, right? So I think when you were born, you guys was born. Can I ask Rahmat Untung? Rahmat, are you listening? Rahmat Untung? I cannot hear you. Maybe I can ask Fabrilia.
Yes, Prof.
So you guys was born in which year?
I'm born in 2002.
2002. Wow, okay. You got very young. Okay, 2002. I was in Nagoya University in Japan. I did my degree, started 1999, and I finished 2003. My degree, bachelor degree, S1 ya. So you guys born in 2003 when I graduated degree, you guys just about 1 year old, right? Okay, so you guys still have a long path to go. So you see, so meaning that when you guys watch the television in 2010, which is you guys like 8 years old. So most of you have this flat TV screen, right? So this is how the TV evolved. So this TV have 3 types. Most of flat TV we have they call as a plasma TV, LCD TV, and LED TV, right? So this is the difference. We have discussed this before. What is the difference between the plasma TV and the LED TV? Okay, so what is the difference with the LCD TV? So so these are the content which I think we have discussed some of the content in the previous lecture, which is about the plasma. What is the fundamental of the plasma? What is plasma, right? What do you have in plasma, and how we can use this plasma as for the plasma processing. Okay, so use this pen is better. Okay, wait. Okay, so when we have a plasma, we need a technique. We need a technique to study the plasma. So we call this as a plasma diagnostic. So this is what we call as a plasma diagnostic. So plasma diagnostic is a tool, a medium, how we can investigate, how we can understand the plasma. So we need a tool, we need a technique to investigate it. For example, when we got for example the COVID-19 right now, right? So there is a tool, right? Rapid test kit, RTK or PCR tools to investigate whether you have a COVID-19 virus or not. So we need a tools in order to understand or to investigate what is the plasma. So these are the tools that I would like to explain. I think it's quite a common or basic tools that we have in this plasma diagnostic. Of course, there are many other tools. So I will discuss about the most common or basic tools. First, on the Lamia Probe analysis, where we can investigate the electron density and electron temperature. And then we have optical emission spectroscopy, so where you can understand the atomic density, electron temperature. And then we have a much more sophisticated technique, which called a laser-aided spectroscopy. So this is much more delicate tools, but we can also understand about the atomic density and the nanoparticle. Of course, these tools have advantage and disadvantage differently. So that's how we can see the content after this. So then we can understand also the correlation between the plasma diagnostic and its deposited thin films. Okay. Berlian, are you? Are you listening, Berlian? Are you?
Yes, sir.
Is it I'm speaking fast? Can you understand, or I need to speak slowly? Is it okay?
Slowly.
I need to speak slowly. Okay, so I hope if you guys don't understand, please do interrupt me, okay? Because it's better for us to have a communication in two ways so that you guys can really understand what is the content of it. So I don't want to just like we call in Malaysia, we call it as a shock sendiri. So I just speaking and then nobody is understanding what I'm talking about. So I need you guys to keep respond. So that's why I try to keep asking whether you guys can understand or not. If you guys need some explanation on the terminology or the terms, I can try to explain. I'm not sure whether I can explain in Bahasa or not. But most of the time we use English because the textbook is also in English. So, but I will try if you want to, okay? So just let me know. Okay, so this is, okay, I think this one I've showed, I'm not sure whether I've showed it previously about the textbook that is available. Like this 3 textbook, I think which is quite very useful. And then we did discuss on this one about the plasma, the difference between the plasma by the medical people and the plasma by the engineers or the physicists. So for us, plasma is a fourth state of matter. So as I mentioned, of course, if you want to recap, the plasma is something that we add energy to the gas. So what will happen is that we can have the ionized gas. So we can have atom, we can have electron, we can have ion inside one space. So that is we call it as a plasma, right? So these are all the example of the plasma that you can see. I think this is just a recap. I think we already discussed also about the Iron Man, about how we can use plasma using seawater to create energy in the future. So these are all the tools in the lab. Okay. So I think this one I'll also discuss. Okay. So when I mentioned about the plasma system, okay, as I mentioned, we have ions in plasma and also radicals. Radical actually is almost as atom, but when we call it radical because sometimes some of the atom is can do reaction. Okay, for example, let's take like oxygen. Oxygen can do oxygen atom is normally we put in the form of O2, right? So you guys are a chemistry student. I think you guys know better than me. But for example, we have O2, we have N2, nitrogen. They can form radicals in the plasma. We don't call as a single atom. We call it as radicals. So they can do reaction. They can do when they encounter the surface like the, for example, steel, ferrum. So it can create ferrum oxide. So because of the oxidation. So this atom that can do chemical reaction, we call as radicals in the plasma. So we can understand, but so radical is but there is no ion, right? So it's not in ionized state, so it's a neutral state. So we call it as a radical. So we can understand what is the density of ion, what is the density of radical. So this is the typical value, which is like 10 to the power of 10 to 10 to the power of 12. Right. So the temperature is also mentioned here. So most of the time, the temperature is in the range of like 2 to 5 eV for the electron temperature inside the chamber, inside the plasma. And also the gas temperature is in the range of 300 to 500 Kelvin. And previously, when we want to control the plasma tools, because last time I think we did show that what we need for the plasma is just we need something like this, right? We need gas, we need a flow controller, we need a chamber, and then we need a power supply to supply energy to the chamber, and then we have something like an electrode inside the chamber, whether it's a grounded electrode or substrate, so powered electrode. So this one is most basic. So we have a vacuum that pump out all the gases, and then we put the gas, and then we put the power supply, and then we create a plasma. So this is how we can create a plasma. So in order to control that plasma, we need to control the power, how many watt that we supply, how many pressure the gases that we supply, what is the flow density, flow density of the gases that we supply, what is the type of chamber, how big is the chamber, what is the brand. So this is how we control the parameter in order to optimize the plasma as a tools for microelectronic or some other applications, depends. So this, the parameter, the control parameter is the most common basic one. But we believe that one is before 21st century. And in the future, we want to make sure that we can control the plasma in much more detail. For example, in the future, we call it as a plasma nanoprocessing, where we can control the density of the atom inside the plasma. We want to control the temperature of the atom or the ion or the electron inside the plasma. We want to control the velocity and the energy distribution of all atoms. So instead of controlling the input power or the input pressure, we want to control inside. So this is much better. So that's why we call it as a plasma nanoprocessing, where we control inside. When we change a different chamber, for example, if you buy a different machine, so you can still produce the same plasma because you understand what is the inside of this plasma, what is the density, what is the temperature, what is the velocity or the energy distribution inside the plasma. So instead of controlling the output or the input that we can inject into the system, we control inside, from inside. So this is much better way. So it's like when somebody have a disease, like for example a cancer, for example. So instead of we do the treatment from outside, if we can do the treatment from inside of our body. So instead of we taking a pill, medicine from we drink it, and then it will go to the whole body. The medicine will go to our heart, will go to our stomach, will go to our hand. So, but the cancer is actually only on our hand. So, but the medicine will go to all area of our body, which is not very effective. So that's why if we can control it from inside, So if we can control the disease from inside, for example, if we have cancer on the hand, so we just want to, we treat the cancer on the hand. So we don't want to control from outside. So that is more important. That's why we are proposing this term in the plasma people are promoting this term as a plasma nanoprocessing. So we want control from inside the plasma. We want control the density, the temperature, and the velocity and the energy distribution. So that's a much more better way for the future. So these are the example of how we can actually optimize the plasma so that we can create a very, very fine or small nanostructure, something like this. Okay. So, okay, this is another example of a very deep trench. So we call this is the cross section, the cross section or of the silicon wafer that used for the microelectronic fabrication. So we can see the very deep hollow inside here that we need to create. So this is why we need a nano processing. So this very deep nano is size of like 250 nanometer, 250 nanometer, or 0.25 micrometer. Okay, so a very, very small size. So our single hair is like, how much is the size of our single hair? If you cut into a cross section of our single hair. Fitri Anissa?
Yes, Prof.
Are you listening? Can you answer me? Do you know what is the size of your hair if you cut it into one single hair? If you cut it, and what is the size of the cross section, the diameter of our hair? Can you estimate? Can you guess? Fitri Anissa?
Yes, Prof. I'm still confused.
How big? Can you understand my question? Fitri? Can you get my question? Can you understand my question?
Yes, Prof. Yes. The answer is no.
The answer is no. I'm asking about the size of our single hair. So for example, this is our single hair. So if we cut the single hair, one single hair, what is the size of the diameter? The diameter of our single hair. Example, maybe you can guess. We don't have the exact value, the exact number. One centimeter or 1 millimeter?
Maybe micrometer.
Micrometer. Maybe like 1 micrometer. I think it's our single hair is like 0.1 mm, 0.1 millimeter, or up to 0.5 millimeter, or something like that, right? So maybe like 100 micrometer. So meaning if our single hair is 100 micrometer, so for this structure, 0.25 micrometer structure, so we can put it up to like how many? For 40, like 40, for example, 40. So for example, we can create 40 transistor inside our single hair. Okay, so that is the technology that we are talking about. I think this is quite an old technology. I think nowadays, inside our single hair, we can create more than hundreds, more than maybe like 500 up to 1,000 transistor inside our one single hair. So that is the technology that we are talking about. So we cannot see from our naked eye. So we have to use a special tool to see it. But we are talking about the technology that can create 1,000 transistor inside our one single hair. Okay, so that is a very sophisticated and critical technique that we need to use. So the roadmap of the plasma is have been published in 2012. So these are the articles that have been published previously. Okay, so these are some of the pioneer of this research of plasma diagnostic. Okay, Professor Saneski from German through University Bochum. So this is Professor Saneski. He quite well known in plasma diagnostic. So I went to this University Bochum one time where I stay over there like 1 month, almost 2 months during the winter. It's very, very cold over there because German is, I think, very cold. And I spent the winter, even the Christmas during that time. So it was very lovely. You can see a lot of shop. I think many people enjoying the Christmas season during that time. So quite very interesting experience that I got over there. So, but anyway, German is also one of the pioneer of for this plasma technology. So where you can see actually plasma technology is used a lot on the coating of the vehicle mechanicals, their cars like BMW, Mercedes. They use a lot of coating. So that's why they have this very strong fundamental of plasma over there in German. So maybe you guys in the future, if you guys thinking of continue your study, I think German is one of the good place to study. So in his article, he did publish about this one, about the plasma diagnostic. So what we have here inside here is a plasma. So we can use emission because we can see the light from the plasma, right? So there is emission. So from that emission, we can also understand about the plasma. We can also have a probe. Probe is we put some needle like this inside the plasma. So then we collect the current from the plasma. So we supply a voltage, we can collect the current so that we can have a IV curve, the current and the voltage curve. So that from IV curve, we can understand what is the electron density, electron temperature inside the plasma. So because as we mentioned, in plasma, you have a free electron moving around. So that will create electricity to conduct the current inside here. So that's why we can use a probe, a needle, a very small needle, because we cannot make it the needle big because it will disturb the plasma. So if the needle is too big, so the needle must be as small as we can. We put inside it, and then we can collect the current from it. So we can also have some other tools. For example, we can have a laser, or we can have a light, LED, a very strong light, inject into the plasma, for example. So then we can see a scattered radiation, which is from the original light, will scattered away. So this also can give us information about the condition inside the plasma. We can also capture the output. So when we put the light inside it, we can capture at the output. We call this as an absorption. So penyerapan. So when we put a light inside the plasma, of course, because the plasma is also a source of light, so some of the light will be absorbed, so become less light will be transmitted, and we can detect from here. So we can check the difference between the input and the output. So meaning that there are some light have been absorbed. So that is how we can understand the plasma also. We can also have some other sensors, right? Like current or voltage or power sensor, so that we supply, we attach to the power input, for example. Okay, so then after 2012, there's another article to propose about the future, the roadmap of the plasma. So 5 years after the first article, I think there's almost the same team. They try to see what is the current trend, what is the future of the plasma. So they published another article. They call it as 2017 plasma roadmap. Okay. So you can see the same, almost the similar team. Like for example, this we have Professor Saneski. I think we also have Professor from Japan. From Japan, we have we have this Professor Hori. So Professor Hori is this guy, Professor Hori. Okay. So in 2017, they try to propose something more new tools. For example, in the plasma, there is a new plasma they call as a microplasma. So then that's why they come with a new idea of this new plasma roadmap to cater the other plasma, like a small scale plasma that have been developed during this 5 years of period. Okay, and we can also now see another article that discuss about the future for the plasma science and technology, where this article actually try to discuss about another application of plasma, not only for the semiconductor industry, where they can use it for the other applications such as environment and agriculture. Okay. So we can use plasma as for the aerospace and automotive. This is quite a common one. We can use plasma for the energy. We can use plasma for the optic and glass coating. We can use plasma as a new technology. We can use this for the plastic and the textile. So we can use plasma for the treatment, on agriculture. Even they can use it for the health, medical, hygiene treatment. So many applications that you can see here. So this is another page to show the application of plasma. So I think this one I've shown before, maybe. So where you can use plasma for the glass, for the flat screen, for the plastic, and for the what else we have? Okay, right. So plasma nanoprocessing. Okay, that's I think this one I will skip. Okay. For the plasma nanoprocessing, we need to understand these three terms because we have the plasma physics, we have the surface chemistry, and then we have the plasma chemistry. So every process is a complex interaction between gas phase chemistry, plasma condition, and surface phase chemistry and conditions. Okay. So for the plasma source, these are the most common source that we can get it in the market. Two type of high density plasma is electron cyclotron resonant plasma, and then we have helical plasma, and then we have this three type of low density plasma, which is called as inductively coupled plasma, capacitively coupled plasma, and magnetron sputtering plasma. Okay. So I think this some of the topic I have already discussed in my previous lecture. So I will just try to skip or just try to keep update and refresh. Okay, this is a ICP type plasma. So where you have the ICP coil, we call it here ICP coil, and then this is various type of ICP. Whether the ICP coil can be at the top, or the ICP coil can be at the side, or maybe the this helical resonator or structure. And then we can also have something like this, detached plasma source. So it's a spiral inside here like this, right? It's like a dome shape as well, right? So this is the type of ICP coil. So they can call it as a pancake structure. This is the top view. We can have a side view. And then we can also have a cylindrical. For example, we have vacuum chamber here. And then we need to have a power that supply to the electrode. To the electrode here, so that we can get a plasma at center. Okay, these are the application of plasma for the wet etching, for the dry etching, sorry. So wet etching is the old version of etching. So dry etching is by using plasma is most suitable for the microelectronic. So as I mentioned, in plasma diagnostic, we can differentiate these two terms, diagnostic and a sensor. Okay. So diagnostic are used in the laboratory, large and expensive, and sensor in use in the production. Okay, this need to pause for a while. Give me 1 minute. Okay, sorry for that. Can you listen to me, Karishma?
Yes, Prof.
All right, thank you. Okay, these two terms, diagnostic and a sensor. So diagnostic is a term that we use in a laboratory. A large is quite most of the time is very large and it's expensive. So sensor is the one that is used in the production. Some is very simple and it's very small. It should be a very less costly. Okay, so for example, we have a lot of sensor, right? For if you have a smartwatch, they can have a sensor to sense your rate, right? Your pulse rate, right? So it can also sense what else? I don't know. I don't have the smartwatch, but anyway, it can sense a lot of things. So there is a lot of sensor inside there. You have a car, you have a motorcycle. Of course, in the engine there is a lot of sensor. Okay, so that is most of the time the sensor will be very less costly. So, but diagnostic is something that is very much bulky and much more expensive. So we want to use this diagnostic and sensor for the plasma nanoprocessing, so that we can achieve what we call as a nano fabrication, right? Maybe jump here. Okay, so there's many tools for the plasma diagnostics. Some of it we can call it as the most simple one. I can call it as we call it as a optical emission spectroscopy. So we just capture the emission from it. And second most basic one is called a Lamia probe. So as where I mentioned, we have to inject a needle inside the plasma, and then we can understand about the plasma property. Sorry for that. And we can also have a laser that's induced inside the plasma. Then we can create a fluorescent so that we can capture that fluorescent for the diagnostic. We can also have microwave interferometry, a much more sophisticated technique where you add the microwave, then we can understand the property of the plasma. We can have a mass spectrometer, so attached to the chamber. So that is some detector, some sensor. Then attached to the chamber, it collect all the particles inside the plasma, so that from the mass, from the weight of that element, so we can capture the properties of it. And then we can have ellipsometry. We can have also laser light scattering technique, another type of laser that we use into the plasma. Then we can have the scattering, and then we can study the plasma. So these are the tools that are widely used for the plasma diagnostic. Okay, as I mentioned, the first and the second one quite simple. You can give a very general property of the plasma. So we do this a lot in our lab. Most of my students do this experiment in the lab. And another technique, they are more exotic, but they can give much more detailed property of the plasma. So we don't have that facilities, that capability of doing this technique in order for our lab. But if you go to the more established country like Japan, German, United States, and even in the Europe, in UK, like you can have these tools. You can experience to try to use this tool for the plasma diagnostic. So first, I will show about the Lamia Probe. So this is the most basic software, the tools that we call as a Lamia Probe. So we can have a needle here. I think the one that you see is the cap, not the needle yet. The needle is very fine over here, where I think the camera cannot capture that. But if you go closely to this cap, you can see the needle. It's like the needle that we use to sew our shirt, for example, right? So it's just a very small needle, the size like 0.1 millimeter, something like that. So quite very fragile as well. So that will be injected into the plasma. Then the software or the computer will collect the IV curve, something like this. So this is the IV curve. So from this IV curve, the current to voltage curve. so you can get the property of the plasma. Okay, so this is a diagnostic tool sold by Hidden Analytical. I think it's an American company. So we got these tools so that we attach it to our plasma system. So you can see on the figure here. So this is the hidden Lamia Probe system. We attach it to this window. This is a window. So we attach it from the side of the chamber. So then we can see the needle. We go inside the chamber, something like this. Okay, of course, we know that the emission inside the chamber. So the tungsten probe, the size is here is we can have the distance from the plasma that I will use for this experiment is we call as a sputtering plasma. So this sputtering plasma have the using a zinc sputter target. So the distance between this tungsten probe to the zinc sputter target is 11 centimeter. So okay. So this is the plasma chamber that we use for our experiment. So we call as RF and DC magnetron sputtering plasma. So we have dual target. So we have 6 viewport. This is one of the example of the six viewport. So this viewport is useful for us to attach with the Lamia probe, to attach with the OES optical emission spectroscopy study. So what is the time now? Anyway, okay, so from the Lamia probe, how is the result that we can get from the Lamia probe? So this is the example. So we issue the probe, we supply into the chamber. So this you can have some circuit. So it depends different circuit. It's showing here. But the most basic one, what we can have is the curve, something like this. Okay, so this is the ideal IV characteristic showing its various parts. So the left, we can understand about the ion saturation. Okay, because the voltage that we supply here is a negative voltage. Okay, so the one that will attract to the needle, to this needle, to the needle here, or the needle here, will be a positive ion. Okay, because we supply a negative voltage over here. Okay, so the positive ion will attract to this needle. So that's why the information that we can have from this curve we call as the ion saturation current. And then we can have the floating potential. We can have the, on the right hand side is the electron saturation current. So this is the transition between the ion saturation to the electron saturation. So if you go in more practical result, so this will be the result. So you can see it's a little bit different, but it just around the maximum current, maybe like 50 nanometer, something like that. Okay, so all right, so then the probe here. Okay, so that. All right, so the probe you can get the current same. This is the ion saturation current. So this is the equation. for the ion saturation current. So where you have this IES is the ion saturation current, if I'm not mistaken. So this is the current here. So from IES, we can get the value of electron temperature, okay, TE here. So because other parameters is actually a fixed parameter. So for example, A is the surface area of the probe, M is the weight of the electron, and 2 pi, we can have it, Ne is the density of the electron. Okay, this is unknown, but first we can get the electron temperature. So we can, after we got the electron temperature, we can get the current the current electron current, and then we can calculate the electron density here. So what I'm trying to say is that by having this curve and these equations, we can evaluate the electron temperature. We can evaluate the electron density here. Okay, so that's how we can understand the property or the diagnostic of the plasma. So we can also understand the ion density from the ion saturation current here. Okay. Okay, so this is the how we can get, this is the equation for us to calculate the ion density. And here, so meaning that from the ion saturation current, so ion saturation current is the current over here. Because it's already saturated, we can see it's flattened. So this is how we can know what is the current at this point. So from this current value in ampere, so we can calculate what is the ion density from ion density inside the plasma. So this is how we can use this tool to understand the plasma. So we can also get the electron distribution function like this. Actually, if you get the system from this hidden Lamia Probe system, actually it's very simple because almost all of the software is automated already. So we just press a button and everything will come out. When I did my study before, we have to do everything manually. So, but nowadays, most of the software is attached to the device already, so you can easily understand or get the result very fast. So this is the example where they apply a different power. For example, they use RF power, and then they supply different power, and then they can see the electron distribution function. Yeah, so we can see from this this result here. So when we change the power from 5 watt up to 60 watt, we can see the distribution of the electron is increasing. So what this curve is giving is the number of electron. For example, the number of electron with the energy of 5 eV. Okay, is on here. So the number of electron of 5 eV increasing if we increase the discharge power. So on the right is also the number of electron with the energy of 20 eV. So of course, the energy of 20 eV, there are not many more, not many compared to the electron with a high energy. So this is the electron with a high energy. It's a lot, but the electron with low, this is the electron with a low energy. This is high in terms of numbers, but the electron with a high energy, the volume is much lower, maybe like 2 orders of magnitude, because this is the log scale graph. Okay, so this is how we can get the result from the Lamia probe analysis, or we can understand it. So this is another example where they use a Lamia probe to investigate the ICP RF discharge, okay, by means of Lamia probe. So you can see they vary the power of the discharge, and then they vary the pressure, 100 Pascal and 200 Pascal. So when they increase the power, you can see that average energy inside the plasma is decreasing. Okay, it's much more critical when we see at the 100 Pascal. This is 100 Pascal. So we can see the decreasing of the average energy is much more drastic for a low pressure. At a high pressure, the energy decrease is not very drastic. So we can easily understand. So why is it happening like this? We can understand, like simple understanding is that when you have a high pressure, meaning that you have many atoms, you have many particles inside the chamber. So that when you have many particles, every particle will collide with each other, will hit each other, right? So when they hit each other, of course, the average energy among them will be almost the same. But if the distance between each particle is far, so they are not frequently hit each other. Not frequently hit each other, there are no contact between each other. So the energy will drop very drastically. So because the average, they cannot be normalized. So that is the reason. Yeah. So by having this Lamia probe, we can understand the property of the plasma. So this is also another example. You can see that they evaluate the electron density. When they increase the power, of course, you can see that the electron density increase. And then they compare with the 100 Pascal and 200 Pascal. So the electron density is much larger when you have more atom inside the chamber, like 200 Pascal here. Okay. Okay, this is another example where they use a Lamia probe to study the plasma in hydrogen. They create a plasma that can use for the solar cell application. They want to create a hydrogenated amorphous silicon. Okay, so this is the film that they want to fabricate, hydrogenated amorphous silicon. So where they use RF magnetron sputtering plasma. So they study using a Lamia probe and the optical emission spectroscopy technique. So this is how the result look like. So they can vary the hydrogen flow rate, and then they study the ion density. The ion density is shown by the, I think, Ni here, the white triangle here. So when the hydrogen flow is increasing, the ion density is decreasing. Okay, so even though the ion density decrease, on the right is a deposition rate. So the deposition rate is almost the same. Okay, they slightly increase for this region. So because at this point is the deposition rate is this. I know when without the hydrogen, which is 0%, 0 SCCM of hydrogen, the deposition rate is here. But when they add the hydrogen, it jumps straight away to this point. So where the deposition rate is very high. So this one is like 1.2 Armstrong per second. This one is like 0.45 Armstrong per second. So they jump up to 1.2, or maybe like how many times? More than 2 times, like 3 times, 3 times increment when they add the hydrogen. So you can see the deposition rate increase. So the deposition rate increased at the first half, and then, of course, when you have the deposition rate increase, we will assume that ion density will increase. So, but from the Lamia result, Lamia probe result, we can see that the ion density is decreasing. So, from this understanding, we can have a conclusion that a high deposition rate was to the silicon target poisoning to become a hydrogenated amorphous silicon that is much more easier to sputter. So that's how we can have the result, and then we can use the result to understand what is the mechanism, what is happening inside the plasma. Okay, so okay, we also tried to, I think the one that I showed just now is some other article that have been published previously. You can find it from the internet. This is not my result, but I just show how the study or the Lamia probe or the optical emission studies can actually be published and get to use this result to understand the property. So in our lab, we did a little bit on this material, which is zinc oxide. So where we put a sputter zinc target on the top, we create a plasma so that from the plasma we can get a zinc atom, we can get the argon ion, and then we can get the oxygen ion or the oxygen atom because we add the gas of oxygen inside the chamber. So one of the major issue to fabricate a zinc oxide thin film, so is on the ion bombardment effect. So we call this ion bombardment effect. So the ion bombardment effect will damage the thin film. So we fabricate a thin film, but because we have too many ions inside the plasma, so that ion will bombard or hit the thin film, so it will get damaged. So this is more critical when we talk about the SAW device, surface acoustic wave device. So where for this device, we need to have a very smooth zinc oxide thin film as a piezoelectric material so that it will reduce the propagation loss. So we need to understand the plasma so that we can reduce this damage and we can reduce this ion bombardment effect. So this is how we use a Lamia probe system. So then we can get what is the ion flux as a function of oxygen flow rate. And then we vary the pressure like a 5 millitorr, 10 millitorr, 15 millitorr, 20 millitorr, and 30 millitorr. So by the flux was calculated from the ion density and also the electron temperature that we got it from the Lamia probe. Okay, so then we can get the flux. So as we can see, when we increase the oxygen flow rate, the flux increasing until it's saturated after like 6 SCCM. And we can see what else? We can see when we increase the pressure from 5 millitorr to 30 millitorr, we can see that the ion flux decrease. Ion flux decrease when we increase the pressure. Okay, so the result actually we double check with another technique where we fabricate the thin film and then we use the tools that call as atomic force microscope. So this is the image. We can see that when we increase the pressure, we can see that the roughness slightly increase. So when the roughness increase, meaning that we got some damage, we got some ion bombardment effect that create a rough surface on the thin film. So this result is consistent with the ion flux analysis. Okay, so these are another parameters for the Lamia probe. Okay. Okay, can we apply Lamia probe at atmospheric pressure? So this is another different topic because in plasma, just now we did discuss plasma in a vacuum chamber. There are also recently plasma that is fabricated at the atmospheric pressure. So they are talking about how we can measure or do the plasma diagnostic on the plasma at the atmospheric pressure. Okay. Okay, another basic technique is we call as optical emission spectroscopy technique. And then from this technique, we can get the atomic density and the electron temperature. So we mentioned in a plasma, you have atom, you have ion, you have electrons that are freely moving around. So for the neutral atom, you have a photon and the nucleus inside here, and then the electron is surrounding the nucleus. And when we add the energy to this atom, to this neutral atom, what will happen to the electron at this orbit? It will jump to another orbit, right? So we call this as an excitation. Okay, we call this as excitation, where the electron jump to another orbit. Okay, so when it jump to another orbit, that orbit is not belong to them. So they are become very not stable. So it's like this is your home, and you jump to another person home. Of course, when you stay over there, you cannot stay for a long time because it's not belong to your home. So you become very unhappy, you become very unstable. So you want to go back to your home. So that is what happening for the electron. So the electron, after it jump to different orbit, it will not stable over there. It will try to jump back to the its original home, to its original orbit. So when it jump to its original orbit, because the level of energy is different, so from the outer orbit to the inner orbit, so it will release a emission, H mu. So these are emission that we will capture. So the plasma got the emission because of this process. So the first process we call as electron impact excitation. So for example, in the case of argon, we are talking about the case of argon. The example here, because argon is the most commonly used gas for the plasma process. It's an inert gas, a noble gas, and quite very cheap to get. So if you will compare to the krypton, xenon, and some other noble gas, which are much more expensive, argon is the most commonly used in the industry and the most cheapest for the noble gas. So the first process is called as the electron impact excitation. So where the argon will hit the high energy electron, and then it got the energy, and then we do the process of excitation. So we use the symbol argon star over here, and then you have electrons. Okay, so when this argon, excited state of argon, want to decay to its original state, so it will release an energy in terms of photon, H mu. Okay, so as the number of photon increase, much more emission that you can see, meaning that you have much more argon excited state. So this is we call as an argon excited state. So Okay, this is the same figure to explain about the optical emission that we can get, the h mu. So you can see the energy band gap, the energy gap for the electron is in this region, the ground state, and then we have the excited state, ion ground state, and then if you get more energy, we'll go to the ion excited state. So if you, and then if of course at the upper level is not stable, so when they want to jump to the lower level, they will emit a light, a lambda here. So that's this is how we can get the emission. So OES is a qualitative measurement of ionic and atomic states in plasma. So we cannot have the exact numbers because of so many parameters that actually affect the measurement or the diagnostic. Okay, this is the typical setup for the OES. You have the where is the chamber? You have the spectrometer, fiber optic, connect to the chamber here. Okay, so of course you have a window over here to capture the emission from the plasma. Okay, this is on the right is the example where you create a plasma. So this is a window over here. You can see a purple color inside that. So that is a plasma. So this is how the example where they study about amorphous silicon, hydrogen amorphous silicon with the power density that we apply to the thin film. So this is the example. You can see when you increase the power, you can see you can get the SIH emission intensity increase. So OES is applied for the ULSI, ultra large scale integrated circuit. Okay, so this is example where in our lab, where we capture the emission of the titanium. So from this emission, we can also understand some of the process and the chemical reaction that occur inside the chamber. Okay. All right. So what's the time? Okay, it's 6:21. Okay, I will try to finish a little bit after this. Okay, is it my explanation is okay?
Yes, Prof.
Okay, wait for a while. Take a break for 1 minute, 1 or 2 minutes. Okay. Okay. Okay, can you see the screen?
Yes, Prof.
All right. I will, I think this one I will skip for the, but these are some slides that I got from the internet where this professor discuss about another tools about in plasma diagnostic of ion sources. So this is a little bit much more focus on niche area. But anyway, I'll just go pass through over here over the slide. And this, I think she's the head of this ITER, which is one of the, I think the project, a mega project in the world about one mega project in the world that they want to produce a plasma, a sun. They want to create a sun. They want to create a sun on Earth. So this is a very big project, but also they need a lot of tools to understand. So that's why they also have a division on this plasma diagnostic. So I will just skip as I think the content is have been discussed early. So okay, this is I think colorful and I think interactive image. So where we can see when we use helium plasma, the color is pink. When we use a neon plasma, the color is red. When we have nitrogen and air, which means oxygen, so on the air, we can see the color of the plasma is orange. If we use hydrogen as a plasma, you can see the color is like a purple like this. So this is information, simple information that we can get from the color. So that is how we can get. So this emission is we can capture using the optical emission spectroscopic technique. So very simple way. Okay, so just skip these things. Okay, so this is another where we can show the plasma that we have in our lab, where we create a sputtering plasma using a zinc sputter target. So you can see when you add the argon only as a gas, so you can see the color is like a bluish color, a metallic mode color here. Okay, so if you use argon and the oxygen gas, so you can see emission is like a little bit purple. So this is we call as a dielectric mode of the plasma. So in fact, we did investigate using a Lamia probe. So where we capture the electron density, we capture the ion density. So this is how we can see the trend or the pattern when we increase the oxygen flow rate, when we increase the gas pressure inside the chamber. So we can see the pattern of the ion density. We can see the pattern of the electron density here. So like for example, this is interesting where you can see the electron density increasing in the first part of the oxygen flow rate in the range of 0 to like 5 SCCM. So if we increase more oxygen, what will happen? The electron decrease. Okay, so this is interesting where we can see that. So when we add small number of oxygen, the electron inside the chamber increase, but when we add too many oxygen, it will decrease. So you have some optimum peak inside here. So what happening here? So we can understand that when we add more oxygen, the issue here is that some of the electron will attach to the oxygen. So it becomes oxygen negative. Instead of you create a positive ion, where the argon ion actually is a positive argon ion. So when you add too many oxygen, it will create another chemical composition of ion, which is called as oxygen negative. So this is because the oxygen can be positive, can be negative. So this is different. For argon, it cannot become a argon negative. So this is electronegativity. So this is difference. Okay. So we can see, we can capture also the OES for during the growth of copper oxide. So you can see the similar trend. So you can see, so this is showing that there are some optimum value of oxygen that we should use in order to optimize our thin film. So we can have a high deposition rate at 4 SCCM. Okay. So another complex tools to investigate the plasma is called as laser-induced fluorescent spectroscopy. So we create a plasma at center here. We inject the laser. So this is the laser. This is some alignment of the laser. So we put the laser inside the chamber. So just across the sputter or the plasma. So then we can capture the fluorescent that created by the plasma and the laser using this ICCD camera. So we have a filter in front of the camera to filter the unnecessary emission. So we want to capture the signal that we want with the ICCD camera. So this is the configuration of the sputter target. I will discuss about the sputtering plasma later in more detail, but this is just some overview of it. So you have the plasma here. Okay, this is this plasma. So for the laser-induced fluorescent spectroscopy technique, we have a laser. So that laser have to be tuned at specific wavelength so that we can capture the atom at that particle level. Sorry, so for example, in this case, so we are trying to capture the titanium atom at 3 levels. Okay, so we know the titanium at the ground state level, there are titanium, they call as titanium A3FJ. J is referred to the here J equal 2, J equal 3, and J equal 4. For J equal 2 is a ground state at 0 eV. For J equal 3 is for 0.02 eV. And J equal 4 is 4.05 eV. So we can use a laser to excite this atom, this neutral atom, to another level. So which is V3F. So this is the number, the name of this energy level for this titanium. So I believe, I'm not sure whether you guys have studied this one. I think this for chemistry people, you know more better. So this is the energy level for this titanium. So we can add the laser at this wavelength so that we can excite the atom at this level to this energy level. So when it's not stable in this energy level, it will go down to another level. So by emitting the emission at this wavelength. So this is our excitation wavelength and this is our observation wavelength. So we use a laser for this excitation wavelength and we use a filter to capture at this observation wavelength. So by doing this, you can investigate a particular or the dedicated particle instead of the optical emission you capture the whole particle inside the plasma. But for laser-induced fluorescent spectroscopy, you can identify which one that you want to investigate, which particle that you want to investigate, which atom that you want to investigate. So that's how we can use this one to capture the titanium atom. We can also use it to capture the titanium ion. So very specific atom that we can investigate. So this is the example of the result. So where we can see the titanium atom at various discharge power, DC power supply that we use for this one. So when we increase the DC power, we can see the atom contribution. So this is the image here showing the density. The density, the blue color is the minimum, the red color is the maximum intensity of the particle. So when we increase the power, of course, we can see the density increasing, right? So, and then in fact, we can understand, we can see the distribution. So this is at 20 millitorr on the top. On the top is 20 millitorr, the bottom is at 80 millitorr. So this is the gas pressure. So we can see, the trend where for less pressure, we can see the atom can move to quite a far range region. So this is the scale here, it's like 7 centimeter. 7 centimeter here. So for less pressure, you can go quite far. For a high pressure, you can see it can become much shorter. So this is what we call as two-dimensional distribution of the atom. Okay. So a little bit complex, but very useful information for people who want to use this plasma for their application to create the coating. So we can also investigate on the titanium ion, the argon metastable state. So it's quite a useful technique. So we can see, for example, here we can see the titanium ion have a lot of density quite far from the target, from the source. The source is on the top here. So the source of titanium. So the titanium ion is created in this region. We can see the effect of the gas pressure. So we can do a lot of things by having these tools. So, and then after we understand the plasma property, we can also relate them with the thin film. So we use the plasma here. We create a thin film at the bottom here. Okay, here we put a wafer. That wafer is connected to some heater because we want to heat it during the deposition. And we can actually capture the ion, the image. This is the trench. This is we did on ourselves. Quite a big trench compared to the previous one that I showed, but the size is 600 nanometer over here. So we can see that we can relate. We can relate the properties of the thin film that we created with the property of the ion inside the chamber. Okay. Also, okay, we can also use this one for this is another tools we call as the, see if I can play this one. Okay. It's not moving. Okay, so the link is not there. Okay, it's not moving. But anyway, this is another tool we call as a laser scattering technique. So again, we can also understand the particle distribution inside the plasma. So you can see here the figure. So this is the figure at various time actually, the various time of the plasma ignition. So 1.3 second, 1.7 second, 42 seconds, like that. So we can understand the distribution at each time. So we have like a video camera to capture it. Okay, so and then we can also relate it again with when we capture the particle, and then we can see the size, and then we can relate with our plasma diagnostic. So this is some of the summary of it. So plasma diagnostic is a window to a knowledge. So by having this plasma diagnostic, we can understand a lot on the electron density, electron temperature, atomic density, at electron temperature, atomic density, and nanoparticles. So actually a lot of information. Having a tools, so plasma diagnostic and its understanding will create us with a better insight of the mechanism, and then we can have this smart plasma nanoprocessing by having this kind of information. So I think that's going to be the end of my sharing for this afternoon. I hope that you guys can get it clearly. So is there any questions? What's time now? It's 6:41. Okay, if I may ask Santa Angelia. Santa, are you listening?
Yeah, sure.
Can you get my lecture? Can you understand? 50% of it? Or how much?
Yes, maybe 50%.
Maybe 50%. Okay. All right. What about you, Nurkolisa? Nurkolisa? Nurkolisa Ramadhani. Okay, so it's not a response. I'm not sure really. Okay, so I think I would like to stop there. If you have any questions on the slide, or maybe something else that you want to ask, not doesn't matter. So Karishma, do we have to take a photo? Because last time I think Dr. Teguh asking about the photo, right?
Yes, Prof. For please on your camera, please. I will take a photo. Oh.
So everybody stay at home or not joining the campus, cannot enter the campus yet?
At home, Prof.
At home. Okay. So when are you guys can join the or go into the inside the campus? When?
Maybe in 2022.
Oh, next year.
January, yes. Next
Oh,
year.
so this year there is nobody is going to go into the campus. So how far is your home from campus, Karisma?
Now I'm in Solo, Prof. I'm in campus.
You are inside the campus.
Yes.
Okay. What about others? Balim Prananta.
Yes, Prof.
Where are you living? Inside the campus?
I'm in the course.
In the hostel?
Course, yeah.
In the course, which is inside the campus or outside the campus?
Outside the campus.
How far? Your campus?
Maybe around 1 kilo.
Oh, very close. Our student in Malaysia, our final year student, master and PhD student, and first year student, they are now joining the campus, go into the campus already. So we allow most of them to come into the campus, but still the lecture is still online, so they can join the lecture inside the campus, so they can use the internet inside the campus. They can go to the library, so they can go to the cafeteria. Okay, are we ready for the photo?
Okay, I will count for 3. 1, 2, 3. Okay.
Okay, thank you.
Prof.